In this video, I'm going to be talking about solving radical equations. But before we get to the radical equations, I want to remind you about a couple of things when you're working with radical expressions. And the first is this. Remember, if you're simplifying something like the square root of 7 times the square root of 7, we know it equals the square root of 49, which simplifies to give you 7. And so we see we really don't need to go through this intermediate step right here and get that square root of 49. So if we have another problem like square root of 5 times the square root of 5, we could go straight to 5. I mean, it's not a big deal on that problem if you went through square root of 25 first, but on another problem like this, the square root of 103 times the square root of 103, it's kind of nice to be able to go right to 103. So of course, if we had something like the square root of 47 squared, that would be equal to 47. Or the square root of 2x plus 1 squared equals 2x plus 1. I just wanted to remind you about how to evaluate expressions that look like that, or simplify expressions that look like that. The other thing I want to remind you about is how to square a binomial and then other expressions that have two terms in them. So remember, if you have 2x plus 7 squared, we can't apply the exponent across the addition sign. We in fact know that it's 2x plus 7 times 2x plus 7, and then you could FOIL that out and get 4x squared. The outside and the inside terms give you a 14x and another 14x, which is 28x. And then the last term would be our 7 times 7, which is 49. And depending on how much you've practiced squaring binomials, you may be able to go straight from the 2x plus 7 squared to the 4x squared plus 28x plus 49. So let's look at an expression like this, the square root of x plus 3 squared. And notice that x plus 3 is not underneath the radical sign. So that's really the square root of x plus 3 times the square root of x plus 3. And we multiply that out much like I did the binomials in the previous problem. So we would have square root of x times the square root of x, which is x. I would have the square root of x times 3 and another square root of x times 3, which makes the square root of x times 6, or 6 square root of x. And then we would have our 3 times 3, which is 9. I just wanted to show you these because squaring expressions that look like this is going to be important in the problems that we'll do in just a moment. Let's practice one more. We'll make it 6 minus the square root of x plus 4. And this time the x plus 4 is the radicand. So if I were to write this out, I would have it as 6 minus the square root of x plus 4 times 6 minus the square root of x plus 4. If we FOIL this out, we have 6 times 6, which is 36. We have a 6 times negative square root of x plus 4, and we have another one of those. Let me just write that out in more detail, since this is the type of problem that sometimes people have a harder time seeing. So we would have negative 6 square root of x plus 4, and another negative 6 square root of x plus 4. And for our last expression, we would have negative square root of x plus 4 times negative square root of x plus 4, which would be positive x plus 4. So if we combined our like terms, we just have the 4 and the 36 that can be combined, and the negative 6 square root of x plus 4 and negative 6 square root of x plus 4 can be combined. We would have this as our result. Negative 12 square root of x plus 4 plus x plus 40. And these are the types of expressions that are going to come up in just a couple minutes. Let's move on and actually solve some radical equations now. Let's let the first equation we're going to solve look like this. It will be the square root of 3x minus 5 equals 4. We're going to take advantage of the fact that when we square that square root, we just get the radicand. So to get rid of the square root, we're going to square both sides of the equation. That's the big deal when we're solving this radical equation. So we would have a 3x minus 5 on the left and a 16 on the right. And now our x is no longer underneath the square root sign. And we just have a linear equation to solve. So we add 5, divide by 3, and we get 7. And let's just check this. Make sure that it actually works. Let's pop 7 into the original equation. We have 3 times 7 minus 5 underneath the radical sign. And on the right-hand side, we have a 4. So let's simplify. 3 times 7 minus 5 is 16. So we have the square root of 16 equals 4, and that means 4 equals 4, and this one checks. Let's look at this next problem. This example will be x to the 1/2 plus 3 equals 11. Let me remind you that x to the 1/2 is equivalent to a square root. So let's write that in radical form. The square root of x plus 3 equals 11. And that line is actually not necessary. You can work with rational exponents if you prefer. But I find often people like to work with the equation in radical form. So when we're solving this equation, we need the square root to be by itself on one side, so that if we square both sides, the radical sign will be gone. So in fact, we need to subtract the 3 first. Subtract the 3 from both sides, and then we'll have the square root of x equals 8. So when we're solving our radical equations, isolate the square root first, and then we can square both sides. So we have x equals 64. Let's check this one as well. We're going to put the 64 into the original equation. So we have 64 to the 1/2 plus 3 equals 11. And simplify. 64 to the 1/2 is 8. 8 plus 3 is equal to 11. So in fact, this one checks as well. Let's do another one. This one will look like x plus 5 to the 1/3 power plus 2 equals 0. Remember, a 1/3 exponent is equivalent to a cube root. So let's write it as the cube root of x plus 5 plus 2 equals 0. As with our previous radical equation, we want to isolate our radical. So let's subtract 2 from both sides, and we'll have the cube root of x plus 5 equals -2. Since we have an index of 3, remember the index is this number right here, we're going to cube both sides. So let's write a cube on the left and a cube on the right. Notice I popped parentheses around it to remind you that it's the entire -2 that's being cubed. So when we cube that cube root on the left, we'll just get x plus 5. When we cube -2, we will have -8. Subtract 5 from both sides, and we have x equals negative 13. Let's check this one as well. We'll pop negative 13 in. Negative 13 plus 5 to the 1/3 power plus 2 equals 0. We're going to see if that's true. Negative 13 plus 5 is negative 8. Negative 8 to the 1/3 is equivalent to the cube root of negative 8, so that is negative 2. So we have negative 2 plus 2 equals 0, and that means it does check. We're going to solve a very similar problem. In fact, I'm just going to change the index. This problem will be x plus 5 to the 1/2 plus 2 equals 0. So when we write this in radical form, it's the square root of x plus 5 plus 2 equals 0. And I mentioned we're going to change the index. And remember, the index is the number right here. You don't see a number, and that means it's a 2. When we have a radical where the index isn't visible, we assume it's a 2. All right, so let's solve this one in much the way we did the previous one. So we'll isolate the square root. We'll square both sides. So we'll have x plus 5 equals 4. We square that negative 2 and we have a positive 4. We subtract 5 and we get negative 1. Let's check this one. We pop negative 1 into the original problem. Negative 1 plus 5 to the 1/2 plus 2 equals 0. So that is 4 to the 1/2 plus 2 equals 0. 4 to the 1/2 is 2. So we have 2 plus 2 equals 0, and that gives us 4 equals 0, and that is a no. Notice that is not true. And that's the big deal when solving radical equations. When we square both sides of an equation, as we did right here, we introduce the possibility of getting a solution that doesn't even work. It does not mean that we made a mistake. It means that we call this answer right here extraneous. Let me write that word for you. This is an extraneous solution, which means it isn't even a solution at all. So we got one potential solution. It doesn't work. That means there is no solution to this equation. But you still need to show all of the steps, show that you got a negative 1 as a potential solution, and then discard it because it's extraneous. So the tricky part is to remember to check anytime you square both sides of your equation. Let's try another one. Let's let this example be 2 plus the square root of 12 minus 2x equals x. So recall our strategy is to isolate the square root first, or cube root or fourth root, isolate the radical, and then either square both sides or raise both sides to the 3rd power or 4th power, depending on what your index is. But we just have a square root here. So let's go. Let's subtract 2 from both sides. So when we do that, we'll have the square root of 12 minus 2x equals x minus 2. Now we can square both sides and take care on the right side. We have a binomial that we're squaring. So on the left-hand side, we're squaring that square root, so we just get the 12 minus 2x. But on the right-hand side, you have to multiply out x minus 2 times x minus 2. You can go to scratch paper and do that, or if you can do it in your head, that's fine. We would have x squared minus 4x plus 4. Do not forget that you are foiling these binomials out. People often overlook the negative 4x in the middle. But notice we have a quadratic equation. Let's set it equal to 0 and see what strategy looks good. I'm going to subtract 12 from both sides, and at the same time I'm going to add 2x to both sides. So I have 0 equals x squared minus 2x minus 8. And that does factor, so let's factor it into x minus 4 times x plus 2. So our potential solutions are x equals 4 and x equals negative 2. Did you notice I said potential solutions? That's because we don't have a guarantee that these are actual solutions. Remember up here, we squared both sides of this equation. That means we introduced the possibility of extraneous solutions. So we need to check these. So we pop 4 into the original equation. Do make sure you go to the original equation. You can't check it lower or later. Sometimes I have people try to check it like down here. Well, we've already done the squaring when we get down to that line, so that's too late. Technically speaking, you have to go up to a line that was preceding the place where you squared both sides. So it's safest just to go back to the original equation. So we have 2 plus the square root of 12 minus 2 times 4 equals 4. Simplify the radicand and we'll have 12 minus 8, that's 4. So we have 2 plus 2 on the left and a 4 on the right. That gives us 4 equals 4, and 4 is a solution. Let me circle that just to be clear. 4 is a solution. Now let's test negative 2. 2 plus the square root of 12 minus 2 times negative 2 equals negative 2. That gives us 2 plus the square root of 16 equals negative 2. That gives us 2 plus 4 equals negative 2. That's a 6 equals negative 2. That is a no. So in fact, negative 2 is extraneous. Let me write that word again. And you need to make it abundantly clear to the reader that 4 is a solution and negative 2 is not. I have done that by circling the 4 and writing and putting an X through the negative 2. Notice I did not obliterate that negative 2. Somebody should still be able to read your work and see that you had it as a potential solution. We could also just write our solution formally in braces right here and say 4 is a solution that way. And then that would represent the fact that 4 is a solution and negative 2 is not. Let's solve this next equation. It will be x equals 7 times the square root of x. Now, I have been saying that we need to isolate our radical first. And I really mean isolate the term that contains the radical. Sometimes on a problem like this, people think that they need to divide by 7. That is not the case. The term with the radical in it is already isolated, so you can square both sides as it is now. If you prefer to divide by 7, go ahead. I don't prefer to, so I'm not going to. So let me show you how it looks if you square both sides as it looks right now. I'm going to square the left-hand side, and I'm going to square the right-hand side. When I square the x, I will just have x squared. On the right-hand side, you do need to take care. Both the 7 and the square root of x need to be squared. So that means I have a 49 times x. But now I'm back to a quadratic equation. We'll set it equal to 0. This one is factorable because I have a common factor of x. So my potential solutions are 0 and 49. Let's check them. Let's pop 0 in. We would have 0 equals 7 times the square root of 0. The square root of 0 is 0. So on the right-hand side, we have 7 times 0, which we know is 0. So 0 is a solution. For the second number, 49, we'll pop that in. We have 49 equals 7 times the square root of 49. That means we have 49 equals 7 times 7, and that is definitely true as well. So this time we have two solutions that both work. When solving a radical equation and when you have two potential solutions, they could both work, they could both be extraneous, or you could have one of each. You just have to check them to find out which case you have. Let's do another one. Let's do it right here. The example will be x equals the square root of 3x plus 7 minus 3. Now the term that has the radical in it is not by itself. It has that minus 3 there. So I'm going to add 3 to both sides. So on the left-hand side, we have x plus 3. On the right-hand side, we have the square root of 3x plus 7. And now we can square both sides. I'll square the left-hand side and I'll square the right-hand side. So I have x squared plus 6x plus 9. Do you recognize where that 6x comes from? Foiling out an x plus 3 times an x plus 3. And on the right-hand side, we'll just have a 3x plus 7. We have a nice little quadratic equation again, so let's set it equal to 0. So we have x squared plus 3x plus 2 equals 0. This is a nice factorable one. It factors into x plus 2 times x plus 1. So our potential solutions are -2 and -1. We check these, -2. And we have the square root of 3 times -2 plus 7 minus 3. So let's see, the radicand on the right is -6 plus 7. That's a 1. The square root of 1 is 1. So we have -2 equals -2. So that is a solution. -2 is a solution. And -1, we pop that in. 3 times -1 plus 7 is our radicand. We have -1 equals, what is that, 4 underneath that square root. -1 equals 2 minus 3. So we have -1 equals -1, and it is also a solution. Notice on the left-hand side, we had a positive number and 0. They were both solutions. On the right-hand side, we had two negative numbers, and they were both solutions. You cannot tell based on the nature of the solutions whether they're going to be extraneous or not. You can have negative numbers that are solutions and negative numbers that are extraneous. Similarly, you can have positive numbers that are solutions and positive numbers that are extraneous. So you do just need to check them. Let's move to this next problem. It will be x equals the square root of 1 minus 8x plus 2. So it looks similar to the previous example. And we'll begin by subtracting 2 from both sides. Isolate that radical. So we'll have x minus 2 equals the square root of 1 minus 8x. Do you see what will happen next? Let's square both sides. So we have x squared minus 4x plus 4 equals 1 minus 8x. We're going to set it equal to 0 because we have a quadratic equation. That means I'm going to add 8x to both sides. And I'm going to subtract 1 from both sides. So I have x squared plus 4x plus 3 equals 0. When I factor, I have x plus 3 times x plus 1 equals 0. So I have x equals negative 3 and x equals negative 1 as potential solutions. Let me come up here for the check. I'm going to substitute negative 3 into the original equation, and I have negative 3 equals the square root of 1 minus 8 times negative 3 plus 2. So I have negative 3 equals the square root of 1 plus 24. That's 25. So I have negative 3 equals 5 plus 2, or negative 3 equals 7. Definitely not true. So in fact, negative 3 is not a solution. Let's check negative 1. Negative 1 equals the square root of 1 minus 8 times negative 1 plus 2. Negative 1 equals the square root of 9 plus 2. So negative 1 equals 3 plus 2. And again, we get an equation that is not true. So in this case, both potential solutions are extraneous. Be sure to answer the question. When the question says solve, you're supposed to state what the solutions are. So make it clear, there is no solution. Or you could use the empty set symbol. So now you've seen that a problem that has two potential solutions could in fact have no solution at all, because both of those potential solutions were extraneous. This next problem will be a little bit different because there will be two radicals in it. It will be the square root of x plus the square root of x plus 5 equals 5. It is tempting sometimes for people to just square each individual term like this. In fact, that is a big mistake. And let me show you why mathematically it's not true. Let me come over here with an arithmetic problem. 1 plus 2 equals 3. That is definitely a true equation. What happens if I just square each of the individual terms? We would then have 1 plus 4 equals 9, which is definitely not true. So it is not mathematically valid to square individual terms in an equation. The only thing you can do is square both sides. So let's get back to the way the equation was originally. It was the square root of x plus the square root of x plus 5 equals 5. Now the key to this is to isolate one radical at a time and eliminate one radical at a time. So we could subtract the square root of x or subtract the square root of x plus 5 and continue. I'm just going to subtract the square root of x from both sides. So my next equation will be the square root of x plus 5 equals 5 minus the square root of x. And now we can square both sides. And in doing so, look at what happens on the right-hand side. We'll have 5 minus the square root of x times 5 minus the square root of x. And I hope you can see why we practice problems like that at the beginning of this video. So when we FOIL this out, I'm over here on my scratch paper, I would have 25 minus 5 square root of x minus another 5 square root of x. That means we have negative 10 square root of x. And then negative square root of x times negative square root of x is plus x. So here is the result of that multiplication. Let me pop it in on the right-hand side. So we have 25 minus 10 square root of x plus x. And on the left-hand side, we squared the square root, so that means we just have x plus 5. So now our equation has gone from 2 square roots to 1. Let's isolate this square root right here. So that means we are going to need to subtract 25 and subtract x. Let's do that. So I'm going to subtract 25 from both sides and subtract x. When we do that, we'll have a negative 20 on the left-hand side and a negative 10 square root of x on the right-hand side. And now I have the term with the radical in it isolated. So I could square both sides right now, and that would be totally fine. But I notice that negative 10 is a coefficient, and it's my personal preference to divide both sides by negative 10 because the negative 10 goes in evenly. So I'm not even introducing fractions, I'm just making the equation a little bit nicer. So I have 2 equals the square root of x. I much prefer squaring this equation or squaring both sides in this equation. So I would have 2 squared on the left and the square root of x squared on the right. So I have 4 equals x, and we have one potential solution. Let's check it. Don't forget that piece. I'm going to come over here. So here's my check. I pop 4 in, square root of 4 plus the square root of 4 plus 5 equals 5. So we have 2 plus the square root of 9 is 3 equals 5. So 2 plus 3 is 5, so 5 equals 5. That is definitely a solution. Again, if you want to answer it formally, you could put it in braces. You just need to make it abundantly clear to the reader that you have checked for and you know it's a solution. Let's practice one more like this where we have 2 radicals in the equation. So our problem will be the square root of 3x plus 7 plus the square root of x plus 2 equals 1. So we have an equation with 2 radicals in it. Remember, we're going to isolate them one at a time. You can choose to isolate either radical you like. As a personal preference, I usually isolate the one that looks more complex or complicated. So I'm going to isolate the square root of 3x plus 7 first. So that means I'm subtracting the square root of x plus 2 from both sides. My next equation will be the square root of 3x plus 7 equals 1 minus the square root of x plus 2. We'll square both sides now. That will take care of the radical on the left-hand side. So we'll just have 3x plus 7, which was our goal in squaring both sides. On the right-hand side, I'm going to come over here to my scratch paper to square it. So I have 1 minus the square root of x plus 2 times 1 minus the square root of x plus 2. I have 1 times 1, that is 1. I have a negative square root of x plus 2. And I have another one of those. And then I have the negative square root of x plus 2 times negative square root of x plus 2, which is just x plus 2. Let me combine some things before I write them in my equation. Let's see, I'll just put this x first. Then I have a negative 1 square root of x plus 2 and a negative 1 square root of x plus 2, which makes negative 2 square root of x plus 2. And then last I have these two numbers, a 1 and a 2. I'll put those together as 3. So let me write those in my equation. X minus 2 square root of x plus 2 plus 3. Now I'm going to isolate my radical again. So let's subtract x and subtract 3. So our equation becomes 2x plus 4 equals negative 2 square root of x plus 2. Do you see that you could square both sides right now? Or you can take care of the coefficient. I look at the coefficient and compare it to the other side. I see that I have a negative 2 right here. And negative 2 will go in nicely to the 2 and the 4, so I'm going to divide. If I had had an odd number over here, a 3 or an 11, I wouldn't divide. I would square both sides as is. But it's your choice when you're doing the problem, so I'm going to choose to divide by negative 2. Make sure you divide each term by negative 2 on the left. So my equation will become negative x minus 2 equals the square root of x plus 2. We'll square both sides again. On the left-hand side, you have some foiling to do. Go to scratch paper if you need to. If you don't, you can just write it out. So we'll have x squared plus 4x plus 4. On the right-hand side, we'll just have x plus 2. Since it's quadratic, we'll set it equal to 0. X squared plus 3x plus 2 equals 0 will be our next line. Factor x plus 2 times x plus 1 equals 0. And our potential solutions are x equals negative 2 and x equals negative 1. If you recall, we had negative 2 and negative 1 as solutions or potential solutions to a previous problem. And they both worked that time. Let's see if they do in this one. So let's check. We'll put negative 2 in. 3 times negative 2 plus 7 is underneath the square root. And we have the square root of negative 2 plus 2. We're trying to see if that's equal to 1. That's square root of 1 plus the square root of 0 equals 1. And that is 1 plus 0 equals 1. And that's a check. And how about negative 1? I've got to slide this up a little bit. We'll check it. Square root of 3 times negative 1 plus 7 plus the square root of negative 1 plus 2. We're seeing if that equals 1. That gives us the square root of 4 plus the square root of 1 equals 1. That's 2 plus 1 equals 1. That's a no. We get 3 equals 1. So in fact, this time, this number right here is extraneous. So we have negative 2 as a solution, but negative 1 is not. I hope this helps you solve some radical equations.